let's start the next portion of Unit 1, which is the modeling in frequency domain. Okay, so basically, in control system theory, complex functions are represented in S domain, which is called the transfer functions, and are commonly characterized as the input-output relationships of the system that can be described by linear time invariant differential equations. Okay, so let us consider one example of nth order linear time invariant differential equation given by this equation a naught y to the power n. Y to the power n means this is nth differential dn y by dt n plus a1 y to the power n minus 1. So it is n minus 1th differential d n minus 1 y upon dt n minus 1. Okay, so this process continues till a n minus 1 y dot plus a n y. Y dot is basically dy by dt. Okay, and this is equal to b naught x to the power m plus b1 x to the power m minus 1 up to bm minus 1 x dot plus bmx. Okay, so here n is greater than or equal to m. So yt is the system's output, xt is the system's input, and ais and bis are the system's parameters. Okay. So taking the Laplace transform on both sides and using the differentiation theorem, we get a naught s to the power n ys plus a1 s to the power n minus 1 ys up to a n minus 1 s ys plus a n ys plus initial conditions terms involving yt. This is becomes equal to b naught s to the power m xs plus b1 s m minus 1 xs plus bm b2 x s to the power m minus 2 xs up to bm minus 1 s xs plus bm xs plus initial condition terms involving xt. Okay, if we take all the initial conditions are 0, then by forming the ratio of the output Laplace transform ys to the input xs, we get this equation which says that b naught s to the power m plus b1 s m minus 1 plus b2 s m minus 2 up to bm minus 1 s plus bm upon a naught sn plus a1 sn minus 1 plus a2 sn minus 2 up to an minus 1 s plus an. Okay, so gs is called the ratio of polynomials in S, and it is the system's transfer function evaluated with initial conditions 0. Okay, so I want you to take notes, write down these equations in your notebook, denoting all the dates. Write down today's date and start taking the notes. I'm giving you 1 minute time. Proceeding, we can say that the components on the transfer function is that the following remarks on transfer function are in order. The transfer function algebraically relates the system's output to its input. A transfer function allows separation of the input system dynamics and outputs into three separate and distinct parts. A transfer function is a property of the system itself, independent of the magnitude and nature of the input or driving function. If the transfer function of the system is known, the system's output and response can be studied for various forms of inputs with a view towards understanding the nature of the system. If the transfer function of the system is unknown, it may be established experimentally or by laboratory testing. Okay, so you know that the convolution integral and impulse response relationship, ys is basically, if you write this from the previous expression, this expression, you can write down ys is equal to gs into xs. That's what I have written here. So ys is gs into xs, and since the multiplication in the complex domain is equivalent to the convolution in the time domain, so this we have already done in the part where we did the revision of the Laplace transforms. So convolution is basically integral 0 to t g tau x t minus tau d tau is equal to integral 0 to t x tau g t minus tau d tau. Okay, so g, where gt is basically Laplace inverse of gs. Okay, so the output of a system in the time domain is the convolution integral between the input and the inverse Laplace transform of its transfer function. Okay, when the input to the system is unit impulse function delta t, for which Laplace transform of delta t is 1, the Laplace transform of the impulse output, that is impulse response, yields ys is equal to gs, right? Because in that case, xs will be equal to 1. So ys becomes equal to gs. So applying the inverse Laplace transform, yt becomes Laplace inverse of gs, that is equal to gt. So we call gt as the impulse response function or weighting function of the system. The transfer function gs or its inverse Laplace transform, the impulse response function gt contains the same information about the system dynamics. Okay, so let us take an example. The problem is that we want to consider an automobile speed control system as depicted in the figure. Find the transfer function from the disturbance input ws. This is the w disturbance input, and from the reference input rs to the output ys. So r is the desired speed, y is the actual speed, w is the road grade percentage, that is how difficult is the road to be traversed. Okay, so from the diagram you can write down the transfer function. So ys here is basically this signal plus this signal. So this signal is b upon s plus a plus kpahy into ws plus this signal is here. So thus the transfer function from ws to ys upon ws. So we can put rs equal to 0 here. So this becomes b upon this. And if we want to find out the transfer function ys upon rs, you can substitute this equal to ws equal to 0. So ys becomes this. So ys upon rs is this part. Okay, so I want you to write down this, draw this block diagram and write down the transfer functions. Start the block diagram algebra. A system is represented as a block with an input and output and a transfer function. So this is the input, this is the output, and this is the transfer function. Control systems are composed of multiple systems such as plant, controller, sensors, and so on, interconnected to each other through a few more schematic elements. These are summing points or summing junctions like this. This is the summing junction, and the branch points or pick-off points. So this is pick-off point or take-off points. Some common topologies for control systems are cascade, parallel, and feedback systems. So let us see. This is the cascade form in which we have G1, G2, G3 all connected in cascades. So at the top shows the cascaded system for which intermediate signal values are shown at the output. So this is basically if it is RS and this is GS, G1S. So output X2 becomes this multiplied by this. G1S into RS is the X2. Now output at this point will be G2S into X2S. But X2S is G1 into R1. So G1, G2, RS is X2S. X1s, because we are saying that signal at this point is X2, signal at this point is X1. Signal at this point we are taking as CS, so it becomes G3, G2, G1 into RS. So we can finally write that RS, if we take the input as the RS and output as the CS, so the overall transfer function inside the block diagram block is the multiplication of G3, G2 and G1. Okay, each signal is derived by the input signal times the transfer function. Thus, the equivalent transfer function is given by G3, G2, G1s. This is GES, which is the product of the subsystems transfer functions. So let us take one example. So the subsystem's output remains the same whether or not the subsequent subsystem is connected. So suppose this is the system VIS and this is V1S. If we want to write the transfer function G1 as V1S upon VIS, Here you can write down, and here G2S becomes V2S upon V1S. So if you want to add these two together, so you form a circuit like this. So V2S upon VIS is basically G2 into G1. If you actually drive this, so you can go on adding this, and you can add a constant also. So what is the output upon input? What is the transfer function? Overall transfer function becomes V2S upon V1S. So it is K into G2 into G1, where G1 is this, G2 is this. So please note down this diagram, this circuit diagram. So this is the cascade form. If you write the transfer function individually, then you can see that this is the cascade form. 1 upon R1 C1 R2 C2 upon S square plus 1 upon R1 C1 plus 1 upon R2 C2 plus 1 upon R2 C1 into S plus 1 upon R1 C1 R2 C2. If you actually find out the transfer functions, okay. So using the cascade transform G2 upon G2 into G1, you get substitute this. So the last two equations are not same. The before last one has the additional term of coefficients in S in the denominator, and it is correct. Okay. So one way to prevent loading is to use an amplifier between the two networks as shown in the figure at the bottom. The amplifier has a high impedance input so that it does not load the previous network. At the same time, it has a low impedance output so that it looks like a pure voltage source to the subsequent network. So this is another example of a parallel form of block diagram. So if you are having blocks connected in parallel, so output at this point is basically this multiplied by the previous signal. So it is Rs into G1s. This multiplied by the previous signal. So R2 into Rs into G2s. G3s into Rs, and all of them are either added or subtracted. This is a dual symbol which shows that this signal is either added. When it is added, then it is G1 plus G2 plus G3. When it is subtracted, this is minus G1 minus G2 minus G3 into Rs. So the overall transfer function becomes G1s plus G2s plus G3s. A parallel subsystem has a common input and an output formed by the algebraic sum of the outputs from all the subsystems. Okay, so it is basically G equivalent is plus minus G1 plus minus G2 plus minus G3. So note down this. So this is feedback form. This is the actual form. Mostly our systems are represented like this, in which we have an input transducers having transfer function G1. It is fed to a summing junction or summing point or error detector. Actuating signal, which is the error, is generated at this point, which is ES, which is fed to the controller having transfer function G2S. Controller is operating the plant which is having the transfer function G3S and giving you the output CS. One part of the output is being fed back to the input through output transducer H1S, through feedback H2S, and this is fed back to the error detector or summing point. Okay, so at this, if you simplify this block diagram into just one block here and one block here, you get a plant and controller in cascade and feedback in cascade, all of them connected in parallel in feedback form. Okay, so basically if you form the feedback form closed loop transfer function, you can see that from this diagram CS is GS into ES, right? CS is GS into ES from here, and ES is basically RS minus BS. If the signal at this point we are taking as BS, then it is RS minus this signal, and this BS is what? This signal into this signal. So RS minus HS into CS. So substitute ES here. So you get CS is equal to GS into RS minus HS into CS. So you can take this CS on this side and take CS common. So CS upon RS becomes GS upon 1 plus GS HS, which is the closed loop transfer function of the system. Please note down this. This is very, very important derivation. And this is the derivation which you will be encountering for most of the control systems in the the ratio of the feedback signal BS to the actuating error ES is called the open loop transfer function. Huh? So this is basically BS upon ES is the GS into HS. This is the open loop transfer function, and the ratio of CS to the actuating error CS upon ES is the feed forward transfer function. Okay, so it is basically called feed forward transfer function. This transfer function is called the open loop transfer function. All right. So conventions of automatic controllers. So this is the part of the automatic controller. We call this part as the controller. So this is fed to the actuator, which is fed to the plant, which produces the output, which is sensed by a sensor and fed back to the actuating error signal. Okay, at this point, error is being detected. So conventional automatic controllers may be classified according to their control actions as two position or on-off controller, proportional or P controller, integral or I controller, derivative or D controller, proportional plus integral, that is PI controller, proportional plus derivative, PD controller, proportional plus integral plus derivative, PID controller. Okay, controllers may also be classified according to the kind of power employed in the operation, that is pneumatic, hydraulic or electronics controllers. Okay, so two positions or on-off controllers are given by the driver drives the plant with a control signal which has only two fixed positions depending on whether the actuating error signal is positive or negative. So UE is basically U1 for ET greater than 0 and U2 for ET less than 0. So where U1 and U2 are constants. Two positions or on-off control is relatively simple and inexpensive, and for this reason it is widely used in both industrial and domestic control systems. So you can represent this two position controller like this. You have one position and the other position. One is 0, the other one is 1. So binary type of control. Okay. So this is basically differential gap. Usually a differential gap is used which causes the controller output UT to maintain its present value until the actuating error signal has moved slightly beyond the 0 value. It prevents too frequent operation of the on-off mechanism, which increases the life of the equipment. Okay. So you can write down this and you can draw this diagram. So proportional controller is basically written by ut equal to kpet, where kp is the transfer function of the p controller, which is called the proportional gain, which is dimensionless. Physically, a proportional controller is an amplifier with an adjustable gain. Integral controller is represented by ut equal to ki integral 0 to t e tau d tau, where I is the transfer function of the integral controller, written by ki is the adjustable gain of dimension S inverse. Proportional plus integral pi, if you combine these two together, so you get this equation. And if you write the transfer function, you get this transfer function. So this is pi controller. Similarly, we can have PD controller or proportional plus derivative. So in this case, TD dE by dt. In place of integral, we are basically taking the derivative. Okay, so US upon ES becomes KP into 1 plus TDS. TDS is the derivative time. Okay, you can write down this equation. So this is the conventional PID controller. This is again very, very important. So please note down the equations. Combination of proportional control action, integral control action, and derivative control action stands for PID. Proportional plus integral plus derivative controller. So basically it is addition of all these three terms. So KPET plus KP upon TI, integral E tau d tau plus KPTD DET by dt. Okay, from which the transfer function of PID controller is derived like this. Take Kp constant, so it becomes 1 plus 1 upon TIS plus TDS. The block diagram of the PID controller is like this. So let us start the block diagram reduction. So basically, so far we have explored three different block diagram configurations, that is cascade, parallel, and feedback form. For each, we found the equivalent transfer function. In general, these three forms are combined into complex arrangement in physical systems. In that case, we attempt to produce these easily recognized form by performing block diagram reduction techniques, and then reduce the block diagram to a single transfer function. Next, we discuss basic blocks: move right, move left, pass, summing junctions, pick off points, and others operations which exist in block diagram reduction. Okay, so let us take one by one moving blocks to create familiar forms. So suppose this is a block diagram in which we are giving RS as the input and we are having XS as the input to this summing junction. And what we want this transfer function to move back from this summing point, right? So basically we can do that, we are allowed to do it, but what we need to do is that we have to multiply, if we will add a block here and we will multiply that block by GS. Okay. Similarly, if we want to move this block ahead of this summing point, then you can do this. The only requirement is that you have to take 1 by GS at this block so that the output remains same. Okay, so please note down this. So what we are doing here is basically we are multiplying these two signals. We are taking addition of RS plus CS and multiplying it with GS. So you can say that this is also, because the output at this point will be GS into RS plus XS. So basically we can say that GS is multiplied here with RS and GS is multiplied here with XS, and both are fed to the summing point here and output is generated. Here what we are doing, we are basically multiplying RS with GS and we are taking XS with plus sign. So if we want to shift this transfer function after this summing junction, then what you need to do is you need to divide this XS, you need to add a block with transfer function 1 by GS so that output CS remains the same. If you actually do this, you will see that the output remains the same. Okay. So moving blocks to create familiar forms. Suppose we are having this form. We are having RS into GS at this point, and here we are having RS. If we want to shift this block diagram, this transfer function from here to here and here, and we want to add another transfer function here, so we can do like this. Okay. So you draw this diagram also in your notebook. Want to reduce the block diagram into a single transfer function. So how do you do that? Please try this problem yourself using the notations which we have done earlier. So you start one by one. So we are having 3 loops here. Start with the smallest loop and try to reduce this part first. So here you can see that the two G2 and G3 are connected in cascade, and these connection, the resultant of these two are connected in feedback with H1S. So first apply the cascade formula, then apply the feedback formula to reduce this block. So you will get one transfer function here. Then again, that transfer, the overall transfer function is connected in feedback to H2S. Then find out the overall transfer function. Then that transfer function is connected in feedback with H3S. Then all of them reduced to just one single transfer function that will be connected in cascade with G1S. So multiply that overall TF with G1S to find out the complete transfer function, overall transfer function of CS upon RS. So please try to solve this problem in your notebook. Note down this problem. Meanwhile, I'll take your attendance. Note down this problem and I'll take your attendance. You try this problem yourself and upload the solution on Google Classroom. I will create one assignment there.
Ma'am, what will be the timing to submit the numerical?
Today class, by the end of today's class. ये तो बहुत आसान है भाई, देखो तो. इसको पहले आप ये डायग्राम को ड्रॉ कर लीजिए अपनी नोटबुक पे, फिर मैं आपका अटेंडेंस ले लेती हूँ. नोट डाउन कर लिया आप लोगों ने?
हाँ मैम।
चलो मैं वहां पे डाल देती हूँ उसको, गूगल क्लासरूम पे ना।